Good evening, everyone. Thank you for having me with you. It's an honor to speak in front of such great audience. Well, I would like to speak today on the geodesic of deformed Sasaki metric. For that, let me give you a short introduction on Sasaki metric. I believe most of you already know Sasaki metric, but even though I like to recall some basic definitions and notions. So what's a Sasaki metric? Let's start by MG and M-dimensional Riemannian manifold, and TM pi and B the tangent bundle, where here pi is the canonical projection from TM into M. So if X is a vector field on then we have the vertical left xv and the horizontal left xh of x are given as follow. Well, here the basis is related to the local coordinate xi, yi. Wi. So Sasaki has discovered on the tangent bounded TM a new canonical metric defined by S equal g of x, y on the horizontal side, as well as the vertical side, and gs are between xh and yv equals 0. This metric is sort of natural metric, and it is also called diagonal metric. Since then, many authors have largely studied and this topic. I can mention, for example, Dombrowski or Prio. For more details, you can check this two references right here. I recommend them. Well, in the last years, many authors are studied and introduced a new vertical deformation of Sasaki metric. I can see it's significant work that inspired this paper. First of all, I like to introduce the metric of Shigren-Gromov, which is, I guess, the most known metric in this area. Many authors studied this metric in details. And the metric introduced by Professor Mustafa Jah, who chose to deform its Sasaki metric by multiplying G by the function f of x r right here, where f is called twisting function. The metric introduced by Professor Aydin Gizer, who add this part right here to g of x y over an almost anti-parahermitian based manifold. You can check these two references right here for more details. Well, by the same way, we give another vertical deformation of Sasaki metric by using alpha r right here and beta r right here, where alpha and beta are smooth positive functions. We have this condition alpha plus beta r positive. This condition is very necessary for GDS to be defined positive. Well, we notice that if alpha equal 1 and beta equals 0, then GDS is the Sasaki metric. Also, if beta equals 0, then GDS is one case of Sasaki metric. If alpha equal beta equal 1 over 1 plus r, then GDS is shear Gromov metric. Of course, the first thing we're looking for is the corresponding Davood connection. In this case, which is verified, the following relations in here. For the proof, I'll use the causal formula, and we use also the fact that G of ZW equal this factor right here, multiplying GDS ZVWV. This relation between GZW and GDS ZVWV is very important for calculation. So what about the curvatures? Using the Levi-Civita connection, we can get the following proposition describing the behavior of the tensor curvature with respect to TM GDS. And we can note that in Formula 1, and to have a relation between the tensor curvature on TM-GDS, the tensor curvature on MG, which is good. But fortunately, on the vertical left, XVYV, have something else. We have a long term in here, and we notice that there is unfortunately no air slide. But I guess this is not a problem. We consider the sectional curvature for P, which is given by the formula for right here, where P denoted the plan spanned by X cubed by T. So if we take Ti an orthonormal frame ITX such that T1 equals W over the norm of W, this family right here is an orthonormal basis on TPTM. Using this frame, we can get the values of the sectional curvature. Question, the sectional curvature, can it be constant? So the answer, if it is, then it must be 0. Way from the formula number 2 here. We put 1 equals 0 and 3 equals 0. We get M is locally flat. So it's say the formula number 4 equals 0 and the formula number 5 equals 0. So the answer will be, if it is, then K must equal 0 and locally flat, and we should have this system here. I think we are certain that in Shiger gramometric, the sectional curvature it's never be a constant. Honestly, I'm still working on the system. I hope I will find something different with this metric. So now we give the relation between the scalar curvature on MG and the scalar curvature on TM-GDS, which is given in the following theorem. And we can study some particular cases. I choose in here the case where M is locally flat, and we can notice that the scalar curvature in this case equals this equation. So can the scalar curvature be a constant? So if M equals 1, then it is the scalar curvature equals 0, and M equals 2, we need to study this side of the equation. The second part is the geodesics on the tangent boundary TM with respect to GDS. So if we take XT smooth curve on T, then any curve CT which equal XT ZT TM, we have C point equal the horizontal left of X point plus the vertical left of nabla X point Z. This is important. For the proof, we can use D by point X equal H plus nabla XYV. Next, we try to give a necessary and the sufficient condition for CT to be geodesic, and we found that CT is a geodesic curve if and only if the system A is verified. For the proof, we use the value of nabla DC C point, and of course, don't forget to replace C point by this formula, right? Okay. Now we can study some particular cases. For example, if we take CT horizontal left, then which means that nabla X point Z equals 0, have CT is a geodesic on TM GDS, and only if XT is geodesic on MG. Second case, if we take CT equal XT X point T, which is called natural left of the vector, the curve XT, then XT is a geodesic on G. XT is geodesic on MG. We have CT is geodesic on TM GDS. And notice that if we take a horizontal left curve CT, we have nabla x point z equals 0, and this gave us the value of zt, which equal in this case exponential to minus integral at dt multiplying k, where k in this case is a constant. This remark allow us to build several examples of geodesic curve over TM-GDS. I choose one example to show you. So if we take m equal r, equate with the metric g equal exponential dx exponential x dx squared, then we have the gamma equal 1 over 2, and xt, the geodesic curve xt, taking the equation x double prime plus half of x prime to squared equals 0. And the solution of this equation equal a plus 2 ln bt plus c, here a, b, and c are real numbers. So we can construct a geodesic curve on TM-CT by putting xt right here and zt right here. In the last part, we talk and we study the geodesics on the unit tangent bounded T1M. So what's T1M is an hypersurface on TM, which defined by the norm of W2 squared equal 1. In this case, the unit normal vector to T1M is given by W over squared lambda V. So the connection on T1M equal the connection on TM minus this term right here. Well, this term is an orthogonal part of T1M and is also called the second fundamental form. In our case, this part equal rho W. So using this notation right here, we found that CT is a geodesic on T1 if and only if the system is verified. In here, rho is some function. So as natural question, can we determine this rho? Answer will be yes by using the following remark. As we know, we have the norm of z squared equal 1, then z prime z equals 0, and g double prime z equals minus norm z prime squared. We obtain rho equal minus 1 plus b, which means is a constant. Therefore, rho is a constant. Now we try to characterize the geodesic curvatures on T1M. So we work on mg local symmetry, which means that r equals 0. So if we take CT geodesic curve on T1M, we have z prime is parallel along the. Also, we have x2p is a constant. For the proof, of course, we derive the norm x2p squared equal to gx plus 1 xp, and xp plus 1 equal rz z prime xp. Switching these two components right here, we found 0. Theorem, we prove that all the geodesic curvatures are constants of eta, of course. For the proof, we can use frame along eta, and we use also the previous result on xp right here. For perspective in the forthcoming works, we can characterize the harmonic and the biharmonic vector field with respect to GDS. Also, we can study some harmonicity of some canonical projections or inclusion of GDS. You can study also the geometry of this deformity, the geometric, or any complex structure, for example, the Calorian. Here are some references that I use for this work. Thank you for attention. If you have any questions or comments, please let me know.